so this video is on 4.2.1, implicit differentiation. I normally start this class with having students do a warm-up. There are 4 equations right here. Only 2 of them are we able to find dy dx for right now. If you want to try on your own, go ahead, pause the movie, and see if you can figure out which 2 we could find dy dx for. All right, the answer would be this one and this one. The reason we can find dy dx for those ones is we can get y by itself. For this one on top, we can rewrite that as y equals negative 2x squared plus 5x plus 9. All right, just moving that 2x over to the right, and then y prime is pretty easy. It'd be negative 4x plus 5. Done. This one right here, we can find out, get y by itself pretty easily there by dividing by 2x. So I could write that as y equals 10x plus 4, all divided by 2x, which if I like, I can rewrite, I can divide each of these by 2x. I can make that 10x divided by 2x is 5, plus 4 over 2x. And if I want to do some calculus, I would probably rewrite that as 5 plus, well, you know what, I'd probably leave it like that. Oh yeah, no, I would. I would divide that 4 and 2. Oops. 4 divided by 2 is 2, so 2 over x. And then I would finally rewrite it as 5 plus 2 times x to the negative 1. So when I want to find y prime, derivative of 5 is 0. Derivative of 2x to the negative 1 would be negative 2x to the negative 2. That took a while, a lot of rewriting, but it's not bad. All right, the reason we can't find the derivative of these ones right now is because I can't really get y by itself very easily or at all. And that's going to be a problem. So when you can get y by itself, like that one and like that one, on all of these actually, when you can get y by itself, that equation, once y is by itself, is given a name. Those are called explicitly defined functions. Explicitly defined functions just has your variable y equal to some other combination of your variable x, right? Y, basically anytime you write it as a y equals to equation. All of these ones on the left are not written as a y equals to equation. They all have a mix of x and y's on both sides of the equation. When they're written like that, they are called implicitly defined equations. Now, implicitly defined equations are a little bit different than explicitly defined equations, right? Because you got that mix of x and y. And sometimes, like this one and like this one, you can't really change it into an explicitly defined equation. You can't get y by itself. Sometimes you're just kind of stuck with the way it is. So what we're going to be talking about today is how I can find the derivative of ones like this that are implicitly defined. All right. So some background information. When we've been taking the derivative, we've actually been taking the derivative of both sides. You just haven't noticed because the derivative of y is dy dx. So for example, when I find the derivative of y equals x cubed plus x, the derivative of y is dy dx, right? That's the derivative of y. The derivative of x cubed plus x, that is just 3x squared plus 1. So we get the derivative of y, dy dx, equals 3x squared plus 1. Now that should have hopefully been easy, but on the next page, I'm going to show this exact same derivative again, but this time I'm going to show you some hidden steps we didn't bother to write down. All right, so on this side, we're going to take that same derivative of x cubed plus x, right there. But we're going to show all the steps. So the very first thing is, if I want to take that derivative, I got to take the derivative of both sides. So d dx stands for the derivative with respect to x. So I'm taking the derivative with respect to x of both of those sides, both of y and of x cubed plus x. Didn't change this at all, same thing here. But this one here, I split into two because of that sum rule, right? The sum rules for derivatives say if I'm taking the derivative of a sum, I can take those derivatives separately. So I'm taking d dx of x cubed, and I'm adding d dx of x. Again, d dx stands for the derivative with respect to x. Now, here's the big step here. From here to there, derivative with respect to x of y is dy dx. It's literally asking how fast is y changing with respect to x, and that's dy dx. On the right, change color here. On the right, the derivative with respect to x of x cubed. All right, well, this is actually a form of the chain rule that we never bothered writing down, and here's why. So the chain rule says when I have something cubed, you bring that 3 down, drop the power by 1, and then chain rule says multiply by the derivative of the inside. Well, you notice how the derivative with respect to x of y is dy dx? Well, same thing here. The derivative with respect to x of x would be dx. Just like here, right? The only difference between this one here and this one there is this one has a y and this one has an x. When it has a y, you have dy dx. When you have an x, you have dx dx. The reason we never write that down is dx dx is just going to pretty obviously be 1, right? dy dx is asking how fast is y changing with respect to x? Well, y might be changing faster or slower than x. So it's a derivative, it gives me slope. dx dx is how fast is x changing with respect to x, right? And that's, well, it's x is itself. It's going to change at the same speed. That's going to be a 1-to-1 ratio. That's always going to equal 1. So we normally kind of ignore that dx dx and we don't write it. We'd be technically correct in writing it. It's just why would we bother? And so anyway, if I did write it, dx dx is 1, dx dx is 1, I get the same derivative, but I did it in a whole lot more steps. Now the question is, why would we ever do it in that many steps? And the answer is, we wouldn't. But being able to see those steps makes implicit differentiation a little bit more understandable. So here we're going to take the derivative of y squared equals x cubed, and we're going to find dy dx with this idea of implicit differentiation. So same thing, we're going to show this step by step. Derivative of that side, well, derivative of y squared is 2y, but then I have to multiply by the derivative of the inside. The derivative of y is dy dx. On the right side, I've got x cubed. Well, the derivative of x cubed is 3x squared. But then if I wanted to, I'd have to multiply by the derivative of the inside, which is dx dx. Now we'll notice typically anytime when it's x, dx dx is 1, so that's just going to go away. So we normally don't bother writing it. But that dy dx is important to write because that is not 1, right? That's the derivative of y with respect to x. If you can do that slope, if you can do that step, all of a sudden you can say here that you've got 2y times dy dx equals 3x times essentially 1. So I don't need to write that. So here it is rewritten without it. And the whole goal of this problem was to find dy dx. Well, there it is, dy dx. If I want dy dx by itself, divide both sides by 2y. There's my derivative, dy dx. You'll notice that dy dx has a y in it along with an x in it. That's not a problem. It's still the derivative. The derivative with respect to x just happens to be an equation that is defined with both an x and a y in it. That's not a problem. To show you how it's not a problem, here we go here. So y squared equals x cubed. We just found the derivative of that. Here is the graph right there. That is a graph of y squared equals x cubed. If I wanted to find the slope at this point, 1, 1, well, here is the derivative I found earlier. Derivative gives me slope. Plug a 1 in for the x, plug a 1 in for the y, and I'll find my slope. In this case, dy dx would equal 3 times 1 squared all over 2 times 1, right? plugging it into my derivative function, which would just be 3 over 2. Derivative, the slope right at that point, is equal to 3 over 2. What if I wanted to find the slope at that point? Well, plug that point in. dy dx at the point 1, negative 1, plug a 1 in for x, I'd have 3 times 1 squared. Plug a 1 in for the y, I'd have 2 times negative 1. That ends up being a negative 3 halves. Slope right there, that makes sense. That definitely looks like it's going downward. Downward slope, slope equals negative 3 halves. Can you see why it's important that this particular derivative is defined with both an x and a y in it? Well, that point had an x equal to 1. That point had an x equal to 1, but they were definitely had different slopes, right? Which slope I had, whether it was a positive 3 halves or negative 3 halves, really depended on if I had a y value of 1 and I was up here, or a y value of negative 1 and I was down there. This type of graph would actually require both an x and a y coordinate in order for me to tell which location I'm at, so I can find the derivative or the slope at that point. All right, let's do a few more examples. All right, so note this technique of differentiating without first solving for y is called implicit differentiation, again, because they are implicitly defined equations. Let's try a few. All right, this one. Find the slope of the circle x squared plus y squared equals 25 at the point 3 comma negative 4. All right, well, first I'd have to find my derivative. I'm going to write my equation down here just so I can more easily see my steps. All right, let's do it. Derivative of x squared. Well, that's 2x. Now, technically, it's 2x times dx dx because derivative of the inside is dx dx, but I'm not going to bother writing that because dx dx is always going to be 1. So anytime there's an x there, I'm just like, oh, derivative of x squared, that's 2x. But if it's a y, then I'm going to be more careful. So plus derivative of y squared, same thing, 2y. But chain rule says then times the derivative of the inside. And the derivative of y with respect to x is dy dx. So times dy dx. Equals derivative of a constant is 0, so equals 0. I wanted to find dy dx because that tells me slope. So just get the dy dx by itself. This one, 2y times dy dx would equal negative 2x. All right, moving the 2x over. Divide both sides by 2y, and dy dx will equal negative 2x over 2y, which if I wanted to simplify that, negative x over y. All right, that tells me my slope at any particular point. This equation wants to find the slope of the circle at the point 3, negative 4. Hold on, there we go. So plug a 3 and a negative 4 in. Slope at the point 3 comma negative 4 would be equal to negative x over y, because that's the derivative. That gives me my slope. In this particular case, a negative 3 over a negative 4, which is 3/4. That's all there is to it. We're going to do a few more just to get the feel of it, the hang of it, and then there's going to be one more oddball thing at the end, I think. Actually, yeah, no, mostly it's just this. One reminder at the end, but let's get through this. Okay, so here are all the ones we did before as the warm-up, right? Same 4 equations. We're going to just work through these with implicit differentiations as examples. I would encourage you to pause each time and try it on your own. So this one, if I were to ask you to find the derivative for this one, I wouldn't do it implicitly. I would just say get y by itself and then find the derivative as normal, because that's the easiest way and the quickest way. We could do it implicitly, but let's actually skip this to save time. That one, we're going to need implicit differentiation. Be careful here though. This is a product. It's 2x times y. So remember the product rule. So when I find this derivative, I am going to have to do it as first times derivative of the second plus second times derivative of the first. Product rule. All right. So finding that derivative, first is 2x times the derivative of the second. Derivative of y is dy dx plus the second is y times the derivative of the first, derivative of 2x, that's just 2, equals derivative of that side. That's easy. Derivative of 10x is 10. Derivative of 4 is 0. So that's just 10 on that side, right? So watch out for things like the product rule and the quotient rule. We still need to keep those in mind. All right, I want to define dy dx. So just get dy dx by itself. Let's see here. This would be 2x times dy dx would equal, moving that y over there, I'm going to write it as 10 minus 2y. If you prefer negative 2y plus 10, same thing. I put the 2 in front, of course, because it looks nicer that way. Divide both sides by 2x. dy dx would be 10 minus 2y all over 2x. That is technically correct. If this was a multiple choice question, they would probably simplify it. All those terms are divisible by 2. So if we divide everything by 2, we get 5 minus y all over x. There it is. All right, let's try a couple more. This one, all right, take the derivative. Derivative of 2y. Well, if it was a 2x, the derivative would just be 2. So the derivative of 2y is 2, but then chain rule says I have to times by the derivative of the inside. So the derivative of y is dy dx equals derivative of x squared is 2x. If I wanted to put a dx there, I could, but I'm not going to because that seems silly. Plus, careful here, derivative of sine is cosine. So derivative of sine of y is cosine of y, not cosine of x. There's no x there, it's a y. So it's cosine of y, but then times dy dx. Why dy dx? Because inside that sine function was a y, and the chain rule says anytime you take the derivative of a composite function like that, you take the derivative of the outside first, derivative of sine is cosine, and times by the derivative of the inside. Derivative of y is dy dx. All right. The whole point of this is to get dy dx by itself. Some people may get flustered a little bit because there's a dy dx there, and there's a dy dx over here, and they're like, I don't know what to deal with that. It's not so bad. To take care of that, let's get all the dy dx's on one side. So I would rewrite this as 2 times dy dx minus cosine of y times dy dx equals 2x. I've got 2 terms there. Both those terms happen to have a dy dx, so factor the dy dx out. If I factor a dy dx out, I'll be left with a 2 from the first term minus a cosine of y from the second term. That'll equal 2x. I wanted to figure out dy dx, so get it by itself by dividing. Dy dx would be 2x divided by 2 minus a cosine of y. There it is. All right, one last example, and then just a real quick reminder at the end about something else. This one says, find the slope of the curve at the point 1, 2. This would be just an example to try and make sure you've got it down. I would recommend trying it on your own. I'm going to start it now. All right, first thing is a product again. Remember your product rule. First times derivative of the second. So 5x times the derivative of y is dy dx. Plus second times the derivative of the first. Second is y. Times the derivative of 5x, that's just a 5, equals derivative of 2x cubed, that is 6x squared, plus derivative of y cubed is 3y squared. All right, same rules as with an x, but then because of the chain rule, times dy dx. there's my derivative. I want to get the dy dx by itself. So let's move all the dy dx's on one side, move everything that's not a dy dx on the other. I would probably write it like this, 5x times dy dx. Parentheses are not, same thing. And I would move this over there by subtracting. So minus 3y squared dy dx equals, I'm left with a 6x squared on this side, but I wanted that 5y over here. Writing the 5 in front is probably a nicer way to do it. So I'm going to subtract it from both sides. Minus 5y. 2 terms, both of which have a dy dx. So factor out the dy dx. Be left with a 5x minus 3y squared. That's equal to 6x squared minus 5y. So my final dy dx would be 6x squared minus 5y all over 5x minus 3y squared. That is my derivative with respect to x. However, I wanted to find the slope at a particular point at the point 1, 2. So to find the slope at the point 1, 2, just plug a 1 and a 2 in. The slope at the point 1, 2 would be 6 times 1 squared, plugging out 1 in for the x, right? Minus 5 times 2, plugging a 2 in for the y. All over 5 times 1, again, plugging a 1 in for the x. Minus 3 times 2 squared. All right, on the top, that'd be 6 minus 10 is negative 4. On the denominator, 5 minus, that's 12. 5 minus 12 is negative 7. Negative 4 over negative 7 is the same as positive 4 over positive 7. Looks like my slope is 4/7. Next page checks. Look at that. Here is the equation of that crazy 5xy equals 2x cubed plus y cubed. This is actually kind of a weird graph with a loop in it. Notice it's not even a function, but even though it's not a function, it doesn't matter. I can still find the slope at that point, 1, 2. It's going to have a slope of 4/7. We got it right. All right, that is implicit differentiation. If you are a person that likes having rules, like a process to follow, here's what we did. Differentiate both sides with respect to x, collect the terms with dy dx on one side of the equation, factor out the dy dx if you need to, and then solve for dy dx. Get dy dx by itself. So if you like step-by-step processes, that might help you out. The only other thing is a quick reminder, there's going to be a few problems on today's homework, like this and like this. This is just a quick reminder because it's been a while and sometimes students forget. If you are asked to do that, that's not implicit differentiation at all. There's no y in there that I need to worry about. It's just saying, hey, take the derivative of the square root of x to the 7th. So don't forget, if you wanted to take that derivative, I would recommend rewriting it. It'd be the same as the derivative of x to the 7/2, right? Which in this case would just be 7/2 times x to the 5/2, because I got to subtract 1. 7/2 minus 1 is 5/2. This one I would rewrite as a derivative with respect to x of x to the 4/5. So then derivative is a lot easier. Bring the 4/5 down. That'd be 4/5. X to the subtract 1 would be negative 1/5. So just a quick reminder that that's how you do those things. If you've got a square root or a fifth root, rewrite it as a fractional exponent. It makes finding the derivative a lot easier. All right, here's your assignment. Good luck.